Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 7 on categorical data analysis for the analysis of multinomial data using the goodness of fit test. So multinomial data is a generalization of what we've been looking at so far with binomial data. Binomial data has two responses, that's the bi, either success or failure. For multinomial, it's a generalization, so instead of having only two categories your random variable can fall into, you can now have more than two variables. And we'll look at a motivating example using jury pool data. So if we are going to, in this country, be tried before a jury made up of our peers, we need our peers in the jury to be representative of the population, of the population around us. So this data was actually used as evidence in a court case of court cases. The data represent a sample of 1,336 individuals from jury pools in a large municipal court district over a 3-year period in the 70s. And here, the fairness of the representation of various age groups on the juries was being contested in terms of the proportion of older versus younger people. And the strategy for doing this was to challenge the representativeness of the pool of individuals from which the jury was drawn. And this was done by comparing the age group distribution within the jury pool against the age distribution in the district as a whole, basically from census figures. So you look at the census numbers, and so here's all the data for what we observed in the jury pool as well as in the census. So here's age groups, and we've got 7 age groups here. We've got young people, 18-19, and we've split the people in their 20s into 2 categories. And we've got decades for the 30s, 40s, and then the 50s through 64, and then everyone from 65 and up. So we got those 7 groups, and of the 1,300 people, here are the observed counts in those categories. Right? So we have very few young people, but that's also expected because we have smaller age ranges for those younger groups, and so on. All right? So that's the observed counts. If you divide each of these numbers, each of the observed counts by the total, then we get observed proportions. So about 1.7% of people were 18 to 19, about 7% were 20 to 24, 10% 25 to 29, and so on, right? And we effectively want to compare, do the proportions we observed in our jury pool, are they equal to what we see in the census? So every decade we get census numbers, and here we had 6% in the 18 to 19 range, 15% in the 20 to 24 range, and so on. So we want to know, do these pairs of numbers equal each other between what we observed and what we expect? Okay, so we have 7 proportions that we're testing simultaneously, whether they're all equal to each other. And we could find evidence that the data is consistent with the null. So the data here are the observed, and the null is the census proportions, in which case that says that all these pairs, these 7 pairs of proportions, are equal. And then there's lots of ways that the null hypothesis can be rejected. One of the groups could have different proportion. There could be or multiple combinations of these proportions could be different. So that is our challenge to make that test. And the name of this test is called goodness of fit. And the name comes from how good, speaking very loosely, how good do the data proportions fit the population proportions, or the hypothesized data, hypothesized population proportions. So that's the goodness of fit test. All right, so in general, here's the situation. We've got R proportions. In our jury example, R is equal to 7 categories. So we have 7 population proportions. These are our census proportions in that rightmost column. And the thing about proportions is they have to be non-negative, so greater than or equal to 0, and all the proportions have to sum to 1. In my research, that's called the simplex condition. I do research on mixture problems. And the hypothesis here, the null hypothesis, is that all of the true proportions or in our population equal some specified proportion. Okay, so in this case, the proportion of people in the 18 to 19-year-old category equals the number from the census, which, if I scroll up for a second, is 6%. For the second group of young 20-somethings, that is the population proportion equals 15%, and so on, okay, up to the 7th or last category. And the alternative most simply can be stated as not H naught. So not with NOT and H naught with NAUGHT as the subscript. And so that means that there's any one of these equalities could end up being not equal, and that would reject the null. All right, so we're going to evaluate the plausibility of the null hypothesis by comparing those hypothesized proportions with what we observed. And the observed proportions are the p hats. Okay, so p1 hat, p2 hat, these are the observed proportion categories in our table. So the 1.7%, the 7.2%, and so on. And we're going to use, we're basically comparing those proportions with the hypothesized values. All right, so there are several ways of calculating our Pearson chi-squares statistic. So this, what looks like this letter X is actually the Greek letter chi. It has a straight increasing sloped line and then sort of a curly line going the other direction. That's how you write it. And it has a square on it because there's a square quantity that's being calculated on the right-hand side. So you've seen this actually in Stat 145 when you did two-way tables of association, and we'll see that test later in this chapter. But this statistic is used for this instance as well. So we have observed frequencies, and we have expected frequencies, and I'll show you how to calculate that in a second. And we're going to, so if what we observe is similar to what we expect, then this numerator is going to be small. We're going to divide that by the expected value. And if we add that up over all the R categories, then we've got a bunch of small numbers added together, and our chi-square statistic will be small. That's if our observed and expected are close to each other. If what we observe is actually quite different than what we expect, then our chi-square statistic is going to be large. So small values of chi-squared is consistent with the null hypothesis, and as the chi-square statistic gets large, that's growing evidence against the null hypothesis. Notice that the chi-square statistic's always going to be positive, and only 0 if all the observed are exactly the expected, and that doesn't happen in practice. So how do we calculate O and E? These simplest way for the observed, these are frequencies. So, all right. O is the expected frequency. Notice that this equation here, O equals NP. If you divide both sides by N, you get O divided by N equals P hat. That's how you estimate that proportion. So this is just another way of representing the observed frequency, the total sample size times the proportion in the ith category. So that's the observed frequency. And then E is the expected frequency. And we don't usually see the expected frequency, but we can calculate that based on the sample size and the hypothesized proportion. So if I page up for a moment to that table from our example, In the first category, we have 6.1%, and we have a sample size of 1,300. So if we multiply those two numbers together, we would get an expected frequency. And we would compare that expected frequency to our observed frequency of 23. So the O here is 23, and the E, the expected frequency, is the 6% times 1,300. So I'm going to page back down. There's, okay, fine. So that's our chi-square statistic, and then we're going to compare the chi-square statistic versus a chi-square distribution, calculate a p-value, which is the right tail probability, and that will assess whether the null hypothesis is true or not. There's another way of formulating the chi-square statistic in terms of what's called, I think these are Pearson Residuals. And so these z-squared quantities are actually this whole right-hand side here. So we can look at those z's, and we're going to look at those a little bit later. So z is the observed divided by minus expected divided by the square root of e. So that's just the square root of this numerator right here. That is z. So if you square this quantity, z squared, that's the same as this right-hand side at the top. So we're going to look at the z's a little bit later. We'll see it in a few different contexts. Z is basically, for category I, how different was what we observed from what we expected. And that will tell us for which category was the null hypothesis contradicted. So if we've got 7 categories in the, page up for a second, in the jury example, and there may be some of these categories that are really different from the null hypothesis, and there may be some that are consistent with the null. For example, these two numbers, 0.219 and 0.217, are really similar. So that's the observed and the expected are very close to each other. In this top category, the observed of 0.01 is less than the expected of 0.06. Okay, so this suggests that the first age group is much less. So this will have a negative Pearson residual, the z, whereas, let's say this one, the 50 to 64-year-olds, there's many more observed than we expected. So that older age group is overrepresented in our jury pool. And so that will have a positive z statistic. And so that will tell us, so that z statistic is going to tell us the deviations from what we observed and expected and which direction, negative or positive. Finally, this formula is just another equivalent formula for the observed minus expected at the very top. So effectively, if you divide by n and so on, and put the p's in place of the o's and e's, a same equivalent way of calculating the statistic. All right, so I've told you about all this stuff. When we calculate a test statistic, we're going to do it based on the chi-square distribution, which is a right-skewed distribution. It starts at 0, and it's not like the normal distribution, but it does increase, and then it tails off to the right, very long tail that goes off to infinity. That's right-skewed. Ah, beautiful. This is a chi-square distribution, and one way of looking at this on the left-hand side is we've got a critical value, which will depend on, the shape of this distribution depends on the degrees of freedom, and the degrees of freedom depends on how many categories, and it's one fewer than the number of categories. So we had 7 categories in the jury example, so our degrees of freedom will be 7 minus 1 equals 6. Right. So it'll be, so the shape, the amount of skewness depends on the degrees of freedom. We'll calculate a test critical value that if you're more extreme than this value, then we would reject the null. So this shaded area is the rejection region. Alternatively, we can just calculate the right tail probability from our test statistic, calculate our p-value, compare that to our alpha level, often 0.05, to make the decision from our hypothesis test. So we'll return to this example. So I would like to mention, I'm going to page up for a second, this particular example only has a few numbers. It has the observed counts, so that's 7 numbers, and it has these expected proportions, that's another 7 numbers. And with those few numbers, we're going to create, which I'll judge to be a ridiculous amount of output to make and to interpret this data. So follow with me, but all the input is just 7 plus 7, 14 total numbers. I'm paging back down. We'll return to the jury pool example, and I'm going to call the population proportions for those categories based on the lower age. So for example, P18 is going to be the proportion for the first group, which is ages 18 to 19. P20 will be for the 20-year-olds. P25 will be for the 25-year-olds, and so on. So we've got our null hypothesis that includes all of these 7 proportions. And these are all the census proportions from the rightmost column in the table above. The alternative is that the null hypothesis is false by contradicting one of these 7 equalities. We can calculate the expected value for each category. So that, as I mentioned before, that was the total sample size times the expected proportion. So for those 18-year-olds, that was 6.1%. So it's a 6.1% times the 1,300, which is 81.5. And even though these are expected frequencies, it's fine that we have non-integer frequencies. So for each category, we can calculate the z-statistic by the observed minus the expected divided by the square root of the expected. So for this first group, we have a negative 6.5, roughly, and that's our residual. I will tell you that that's a fairly large residual. Basically, numbers that are more extreme than about 2 units is going to be fairly extreme here. And then for each category, so that's the calculation for the first category, square that z-statistic, and then do that for all 7 categories, add that up, and we get a chi-square statistic of 231 in this case. You might ask if that's big, and I'll tell you that it is huge. Okay, our degrees of freedom are 7 minus 1. Okay, the number of categories minus 1, so 6 degrees of freedom. Our critical value, so the number that our chi-square statistic needed to be greater than to reject the null, was only 12.5. So we are miles away from that cutoff. And if we calculate the p-value, it's going to be very small. It's much less than 0.001. So that gives us sufficient evidence to reject the null. So it appears that there's some difference between the jury frequencies that we observe and what we would expect from the census. So here is a table of the age groups, the observed counts. We had that from before. Now I've put in the expected counts for each category, as well as that z Pearson residual for each of the categories. So numbers here that are close to 0 are where the observed and expected are pretty similar to each other, such as the 30-year-olds. And then the residuals that are far away, either positive or negative, indicate how the observed compared to the expected. So negative residuals here are lower, or the observed is lower than expected, and positive numbers are where the observed are higher than expected. All right, how do we know if we can perform the hypothesis test we just did? Okay, so what's the adequacy or model assumptions for the goodness of fit test? So one conservative rule is that the expected count should be at least 5 for each category. So let's go compare that here. So here's all of our expected counts, and all those in this case are greater than 5. So good. We should feel pretty confident that the result of this test is can be trusted. There's unfortunately there's no widely accepted alternative for a method for doing the goodness of fit test when you've got small sample sizes. There are some non-parametric strategies such as using the bootstrap or permutation tests, but it requires often a little bit of programming to implement those. There's evidence that the chi-square test is slightly conservative, meaning that p-values tend to be a little too large on average, which means that sometimes even if you have enough evidence to reject the null, or your data should reject the null, the p-value might be a little too big, and you may fail to reject the null even though you should have had enough evidence. So just an indication that we're unlikely to reject the null more often than chance would dictate. And some statisticians recommend that the chi-square approximation would be fine as long as the minimum expected count is at least 1 in each category. Sorry, I pressed the wrong button. So rather than 5 in each of these categories, some statisticians say that you need at least 1. So, and there's some simulation studies that say that would be fine. So I will suggest that you have at least 5 in each category, but if you're stuck, you can come back to these notes and use this as a citation, perhaps try to dig up the actual information for that. Let's see what the R implementation of this looks like. So I've created a small table here that just has two columns of numbers. It has the counts and the census proportions, and I have my categories as the ages on the left-hand column. And by default, read.table uses spaces as delimiters, and I'm specifying that I've got a header on there. So we should get a simple table just by reading that in just like that. So when we look at the structure, we've got 7 observations and 3 variables. We've got age, count, and census, and we've got these factor levels. And one note here, these factor levels are always ordered based alphabetically, and because our ages are effectively alphabetical, numerical order, they're going to be in the correct order throughout. So that's good news for us. And here are the data. Nice. So now it's our job then to create some new columns in a moment. We're actually going to do chi-square test first, but in terms of creating some plots and visualizing here, we're going to create some additional columns that we've seen in the tables previous, and all those are fairly easy to calculate, and plotting our evidence such as observed and expected frequencies and the chi-square residuals, all those things can be easily calculated and plotted. So I'm going to show you all that coming up. Here is the chi-square test, and all you need to do is put the vector of counts that you observed as the data. So here's the column of counts. So it's these 7 numbers that are the data. This correction is another thing, just like the Yates correction in earlier sections of this chapter. And we are conducting a hypothesis test. The default hypothesis test is that the proportions for all these 7 categories are equal. If it's not equal, you need to specify those proportions in this way, p equals, and in this case we have the census proportions, which are our null hypothesis, those 7 proportions there. I'm going to put that result into the x.summary. X here sort of looks like the Greek letter chi. And let's take a look at those results. It's actually a very short summary, just one line of 3 numbers. It gives the chi-squared statistic, it gives the degrees of freedom, and then the p-value associated with that test. And this is as small a p-value as will be reported in R. It says the p-value is less than 2 times 10 to the negative 16. So this is a decimal point followed by 15 zeros and then a 2 at the most. So we have major evidence of differences here. From that calculation in the x.summary, there's a bunch of numbers that we can use for creating plots and so on. And so I'm creating a new data frame here that has, in fact, I'll have the have the table here that we can look at the same time as I describe how we're creating it. So we've got, 6 columns. The first one is the age column. Okay, so those are our labels from our original jury data. And then the rest of the columns are from the summary object that comes from using the chi-square.test function. So we have our observed frequencies. That came from the data as well, but it's saved in the x.summary object as observed. We also have our expected frequencies, and it's from those that we could calculate the residuals. But the residuals are already calculated for us. So there's the residuals. Here's the residuals squared, which I'm calling chi-square here. That's just a contribution to the chi-square statistic. So if you add up this chi-square statistic, the 42, 54, and so on, if you add all those up, you get 231. That's our chi-square statistic. And finally, the standard residuals are, you can see that they are quite similar to the residuals. They're sort of a better version of the z statistic that I showed you earlier. All right, so let's take a look at some plots to see which of these age groups were deviated from our null hypothesis. And the first plot I'm going to create, I believe, is the observed versus expected. So here's some code I'll come back to in a moment. Let's take a look at the plots first, and then we'll go back and understand how to create those plots. So let's take a look on the left first for observed and expected frequencies and interpret this plot. We have on the horizontal axis the age groups in years, and on the vertical axis we have counts. We've got red and blue in the legend. The red are the observed counts, and the blue is what we expected under the null hypothesis from the census. And so as we go through each age category, we can see where the differences are. So for the 3 youngest age categories, for people basically younger than 30, the observed in red is less than the expected in blue. So it seems that the young people are underrepresented in jury pools. When you get to 30, we have about equality here. Then the people in their 40s and 50s are overrepresented in the juries. The red observed is bigger than the expected blue. And then in the oldest category, they're about equal again. So that's those are the data and what we expected. On the right-hand side are the contribution to the chi-square statistic. So that's the second term. That's the column above that was the second to the right. It was the residuals squared. And notice that I've sorted this based on the contribution to the chi-square statistic from largest to smallest, and the age is along the horizontal axis. So it's those 50-year-olds who are the most different than the observed, or than the expected, and then the young 20s, the 18s, and the 40s that are most different, and then finally it tapers off to the 30-year-olds, basically are exactly what you expected. So this is this basically gives us evidence for which are the biggest deviations from the expected. All right, so let's take a look at the code for this. Let's start with the second plot, because that one's super easy. No, we'll start with the first plot. All right. So let's look back at this table. The x.table has these columns in it, and we're going to focus on the observed and the expected frequencies. And in order for ggplot to do something with this, we need to take this data that's in wide format. Basically, we have a label for age, and then we have 2 variables that we want to plot. We want to plot both observed and expected. And we need to reshape this so that all of these observations for the observed and the expected fall into a single column. And then we'll need to create a second column, or rather a third column, that indicates whether the number is from the observed column originally or from the expected column originally. And that's what melt is going to do for us here. So from the reshape2 library, the melt function is going to start with the x table, and the variables that identify each row are the age column. The measurement variables that we want to stack up vertically are the values from the observed column and the expected column. And the statistic, so the variable names are going to be under a column called stat, and so that will be the labels observed and expected. And then the values, that is the numbers that fall in the observed and expected columns, will be put into a column called value. And for some reason back in 2012 when I was writing these notes, these labels weren't working. It may actually work, and you might not even need this row anymore. But this was just relabeling the age, stat, and value columns. All right, so one thing to do if you're following along with running this code at home is print out this object in your console and take a look at those columns. All right, so now we've got this table. It's got 3 columns. It's got the ages, which repeat twice. It's got the statistic, which is a list of the letters observed or expected, and then the values are in this third column. And we're going to plot, using ggplot, the data in this table. The x variable are the ages. The fill color is based on statistic, so whether it's observed or expected. And then the weight, that is the values, the height of the bars that we're plotting, are going to be the value. So those are the frequencies for each of those. And so if we scroll back down, we've got the categories along the x-axis. We have the statistic, which are different colors, and the heights are the frequencies. So that's what created the plot. In the last couple lines there, we're just labeling the title and giving a better label for the x-axis. So if I page back up, these are the last 2 lines that I ignored before. So just labeling the plot. Good. On the right plot, recall, there's only one interesting thing happening here, which is that these X categories are sorted in descending order based on the contribution to the chi-square statistic. So we have 2 pieces of code here. The first is we have our X table. So let me scroll up for a moment. Here is our X table, and we effectively want to order the ages based on the column chi-square, and we want to go from largest to smallest. So here's the largest number, 77, followed by 54, followed by, looks like this, 41.9, and then this 41.9, and the last one is going to be the 0.03. So that's the ordering we want for our age categories. We can do that using this line of code here. Okay, so first I'm going to create just a subset of our X table that has only 2 variables, the age and the chi-square. So I've subsetted the X table, and so the square brackets indicate the subset. Before the comma, I would indicate the rows. There's nothing there, so I'm going to use all rows, comma, and then which columns? The age and the chi-square columns. And notice here I'm referring to those columns by name rather than the numbers. You could, if I page up for a moment, refer to them as column 1 and then 2, 3, 4, 5. So columns 1 and 5. But I think that's a little bit risky because it's possible that you come up here and you add a variable or you remove a variable, and then the column numbers change. And so in particular the chi-square might not be in the 5th position anymore. And so it's much safer to refer to these columns by their actual names, because the names are less likely to change than their position. Okay, so now we have a small table that only has 2 columns in it, and we're going to reorder the ages in the data frame based on, so we're going to reorder the ages in descending order, that's the minus sign, based on the chi-square statistic. And so this creates the age variable in that different order, and then when I plot it using ggplot, so this is a very simple bar plot here, this age variable has been reordered, and that is why, if I page down for a moment, it appears in this different order. Okay, so we've seen this example here just now. Also in chapter 0, I have an example where the categorical axis has been reordered. So it's handy occasionally. All right. This is probably a good place to pause here. So we've done the global hypothesis test and the follow-up test. Let me just page down for a moment. You know what? Better just finish it. All right. So just like in chapter 5 when we did analysis of variance, you test the global hypothesis of whether all the means are equal to each other versus not equal. And if you reject the null, then that means that at least one pair of means were different. And then you've got to investigate which pairs were different. Okay? So the same thing here in chapter 7. We have a null hypothesis that there were 7 different proportions that were simultaneously all equal to a specific value. Well, we rejected that hypothesis. So now the question is, which proportions were different? You know, there might have been 1 of these or 2 of these or all 7. And so now we want to separately test each of these hypotheses. So now we've got a separate null hypothesis for every category. These are now become just a bunch of binomial tests. Each category becomes a success, where all the other categories become failure. So for example, if we take this third category, it's a binomial test. It's a success if you are a person between 25 and 29 years old, and it's a failure if you're any other age. Okay? And so in that case, we can estimate the proportion of successes, proportion of people in that late 20s category, and see whether it equals 13.5% or not. All right. So we've seen Bonferroni comparisons in chapter 5 before, where we want to protect ourselves from the Familywize error rate. So we know if we have an alpha level of 0.05 that for each separate hypothesis, we have a 5% chance of incorrectly rejecting the null hypothesis. And so the Familywize error rate corrects for making at least one error. So we have a 5% chance of making an error on each separate one, but now we want the chance of making any number of errors, whether it's 1 error, 2 errors, 3 errors, whatever, any possible error, we want that to be 7% for these 7 tests, all taken jointly as a family. So the simplest and most conservative strategy for doing that is to simply take our alpha level and divide it by the number of tests. So now instead of 0.05 being our cutoff for our p-value, it's now going to be much more stringent. Now you need a lot more evidence. So your p-value for each individual test now needs to be no bigger than 0.007. It needs to be smaller than that to reject the null. It also means that our confidence intervals, instead of being 95%, are now 99.3%. Okay. So I'm just going to scroll down, and I'm going to do, okay, so what did I do for all my code? I'm doing a separate binomial test for every one of the 7 categories. So I'm counting up what was the number of successes for each category. So that's the observed frequency for each category. What's the total sample size? That's adding up all the observations over all the all categories. The census proportion that we're testing under the null hypothesis is the census proportion. We're looking at a two-sided alternative, meaning we don't care whether the observed counts are more or less than the expected counts. And then our confidence level that we're going to construct confidence intervals for are corrected for that Bonferroni adjustment. So instead of it being 95%, or 1 minus 0.05, we're now dividing our alpha by the number of tests. So it's 1 minus 0.05 divided by 7. And that was that number, if I zoom out for a moment and scroll up just a little bit. That's this number here, 0.00071, and corresponds to a 99.3% confidence interval. So the way I wrote this is I wrote this for one group, and then I copied that line 6 times, and then I just changed the 1, 2, 3, 4, 5, 6, 7 going down. All right. And so I'm going to do all those hypothesis tests. Each of them go into a b.sum. The b is for binomial, sum is for summary, and the 1 through 7 are the 7 categories. I'm putting all of those results together into a single summary. I've got all the p-values and the confidence intervals as columns in that table. I'm going to name the columns, the p-value, the confidence interval, lower and upper bounds. And then I'm going to also add to that the age, the observed frequencies, or observed proportions, and then census proportions. And if I zoom in on this, all right, we've got a table. So for all the 7 age categories, we have a p-value testing whether whether we would reject the null hypothesis that the observed proportion is different from the expected proportion. And let's see our results. Youngest group is different, second is different, third is different. So we're comparing these p-values to the 0.007 cutoff. This one is 0.8, so that is not significant. This one is highly significant, times 10 to the negative 7, times 10 to da. And this one is 0.003. That's smaller than, hold on, I keep forgetting. We're looking for 0.007 or smaller. Okay, so I'm paging back down. So this is 0.003, so that's smaller, so we reject there. So we're going to reject all these hypothesis tests except for the 30-year-olds. So we have quite a bit of substantial evidence here that our jury pools are not representative of the population distribution of ages based on the census. Here's that table that looks a little bit prettier. Guess I could have just looked at that one. And basically discussed all of those results. So that's the end of this example. That was, you're very aware of this now, having listened to this entire video. That was a lot of results from a fairly small and simple data set. So here was the original data set at the beginning of the section. We just had our observed counts and our expected frequencies. And from those 14 numbers, we filled many pages to understand whether the goodness of fit test could support or reject the null hypothesis. So I think the main takeaways here are to be able to do some of these calculations. Well, I guess one thing to note is that there wasn't a lot of code. We read the table in. I'm going to scroll through this very quickly. So there's the table. We did the chi-square test and put that into an X summary object. We created a table that had some residual values and the chi-square statistic, and from there we created some plots. And so we frequencies, and then we also reordered, based on the chi-square statistic, the ages to produce these two plots. So then we had something to present to other people and interpret. And we had already, if I page back up again, sorry, we had already looked at the chi-square statistic and rejected the null hypothesis up here. So we knew, paging back down, that these observed and expected frequencies were different. Then we did a follow-up using the multiple comparisons. We calculated what the new critical value would be for our 7 individual tests based on a Bonferroni correction of 0.07. We wrote one line of code for one of the categories and then copied it many times to do all categories. I put all the p-values together in a single table and outputted it in this table. So there's the ages, there's all the p-values. We're comparing them to 0.007, and all except for the 30-year-olds are different from expected. And that was the end. So there wasn't a ton of code, and we got a lot done. So unfortunately, the description of how to do this takes a long time because there's a lot of ideas. But I hope that you are coming away from this with a good understanding of how to make comparisons for multinomial problems when you have multiple categories. Whew. All right. Thanks for sticking there with me. I'll come back for the next section in the next video.